Okay, Momentum and Impulse Study Guide, our last unit test of the semester. So what is conservation of momentum? Momentum, let's write it up here. Momentum is mass times velocity for an object. And momentum is like energy and matter. It is a conserved quantity, so that means that when two objects interact, and mainly we've looked at that through collisions, okay, their total initial momentum, P, equals their total final. So whatever momentum they have at the beginning of their interaction, then they collide with each other, or whatever, they get stuck together, they bounce apart. Their total final momentum has to be the same, as long as no net external force acts on the system. And that would mean, like, if you've got two objects rolling and they run into each other and bounce apart, momentum's conserved. If they're rolling on a surface with friction, then momentum would not be conserved. Okay, the whole thing would look different, because then you've got a net external force that's introducing something new into the situation. Okay, so all right, 1,000 kilogram elephant is walking by at 1 meter per second. By what factor would his momentum change if he started running at 8 meters per second? So since momentum is mass times velocity, if he's walking at 1 meter per second, his momentum is going to be 1,000 kilograms times 1 meter per second, 1,000 kilograms times meters per second. If he starts running, his mass is still the same, but now he's running at 8 meters per second. He's going to have a momentum of 8,000 kilograms times meters per second. So it's going to be, his momentum is going to be 8 times greater when his velocity goes up. Momentum has a direct relationship both with mass and with velocity. So as mass goes up, velocity goes up, or mass goes up, momentum goes up. Also, as velocity goes up, momentum goes up. Okay. Okay. Bowling ball has 25 kilograms times meters per second in momentum when it hits a bowling pin at rest. And then after the collision, the bowling ball has 5 and the bowling pin has 20. Compare the change in momentum for each object. Okay, so, and change is just final minus initial. So the change for the bowling ball, I'll call that BB. It had 25 kilograms and it ends with 5. So 5 minus 25 equals minus 20. Okay, so the bowling ball lost momentum by 20 kilograms times meters per second. The change for the pin had 0, and then it ends with 20. So 20 minus 0 equals 20 kilograms times meters per second. So the bowling ball lost 20, the pin gained 20. Did the total momentum change due to the collision? No. Okay, the total momentum at the beginning was 25 plus 0. The total momentum at the end was 5 plus 20. 25 plus 0 equals 5 plus 20. So the bowling ball, basically in the course of the collision, the bowling ball gave some of its momentum to the pin. That allowed the pin to start moving because the pin was at rest initially. Okay, so that's where we see conservation of momentum, and no external force was interfering in that interaction. Okay, compare these two collisions. An egg is traveling at 15 meters per second when it hits the bare ground and comes to a stop. So that's like the guy throwing the egg in the video, which they showed that over and over and over and over, and it splatted an egg is traveling at 15 meters per second when it hits a pillow and comes to a stop. Okay, and this is one thing that we'll talk about more this week. So, change in momentum for egg A and egg B. Okay. So, egg A, so they have the same mass. They're traveling at the same initial velocity, and then they both come to a stop. Okay. So, for the first one, we're going to have 0.1 times final minus initial velocity. For the second one, we're going to have the same thing. So the change in momentum is the same. Both eggs start off at the same velocity. They both come to a stop. They have the same mass. Okay. Compare the impulse experienced. Well, impulse equals our change in momentum. So the impulse is also the same. Both eggs experience the same change in momentum, so they experience the same impulse. But the force versus time aspect of their impulse is different. Remember, impulse, it equals change in momentum, but it also equals force times time. Okay? So for egg A, it hits the bare ground. Okay? So it's going to have a large force in a short time. Imagine if the egg hits the bare ground and it splats, that's because there's a large force as it hits that bare ground and a short time over which it impacts with the ground. Egg B, which hits a pillow, is going to have a weaker force and a longer time. The time of impact is going to be longer because it's got this pillow. It can like cushion, like instead of splat. Okay. And the force is going to be weaker because instead of hitting a hard surface, it's hitting a nice soft pillow. Okay. So if I drew that out, I might say, or I wrote that out, I might say for A, I had a large force in a short time. For B, I would have a weaker force and a longer time. Okay, both of those are going to give you the same number when you multiply them together. You're multiplying a big number by a small number by a big, but in the end, the impulse is the same, the change in momentum is the same, but the outcome of the impact is different depending on whether you have a pillow versus a bare ground. Okay, let me try and do this one, and then that'll probably be long enough. Square and the circle collide, a closed, isolated system. That means there's no net external force, so momentum is conserved. Assuming conservation of momentum, what would the circle have to have? So before the collision, my momentum is 18 for the square, plus 2 for the circle is going to be 20 kilograms times meters per second. That has to be the same total after the collision. So if my square has 5, that means my circle has to have 15 because I need to add up to 20. So 5 plus something equals 20. The something for the circle is going to be 10 kilograms times meters per second because momentum's conserved. So these two things have run into each other. Their individual momentum values have changed. I talked about that in class. We looked at that with the collision simulation. We looked at that with the collision equations. Okay, so your individual items change, but the total is conserved as long as there's no net external force interfering. Okay, I'll do the other side in the next video.